Simulation modeling of ship operation. To evaluate the performance of the stochastic port system, we implement a process interaction-based simulation model in Java, which simulates ship operations in one- or two-way channels, and a longer one-way channel with a SPAC according to the logic flowchart in section 2. There are basically three approaches that can be used for discrete event simulation: the event-based, the activity-based, and the process interaction approach. Process interaction simulation is a typical discrete event simulation paradigm. Since processes resemble objects in the real world, process interaction simulation is often easy to understand, which is used in HLA, high-level architecture, DIS, distributed interactive simulation, and other object-oriented distributed simulations. Therefore, we apply the process interaction approach to the ship operation simulation model in this study. The process interaction worldview provides a way to represent a system's behavior from the active entity's point of view according to the authors of SIMULA. Thus, a system is modeled as a set of active entities in interaction, and the life cycle of each active entity consists of a sequence of events, activities, and delays. So in the ship operation simulation, a ship is an example of an active entity. Each ship performs the following sequence of activities: arrive at a port area, wait in the anchorage area, transit from anchorage area to berth, get cargo handled, leave the berth and enter the channel, and depart from port. Besides, the model also includes other components providing services for ships, such as anchorage area, entrance channel, and berth. According to the process interaction worldview, an active entity requires special mechanisms for interrupting, suspending, and resuming its execution at a later simulated time. Thus, Java programming language is suitable as it offers at least a SIMULA's coroutine-like mechanism. Therefore, we implement a process interaction-based simulation model for ship operation, SIMULA, in Java programming language, and the implemented Java classes consist of foundational class library for process interaction simulation, piece library, and business class library for ship operation simulation, SOS library, as shown in static structure diagram of classes implemented for ship traffic flow simulation. Piece library is a collection of public classes for process interaction simulation, such as process, entity, queue, and simulation as shown in. The process class is the base class for a process interaction simulation which extends java.lang.thread and provides all of the necessary operations for the simulation system to control the simulation entities within it, and for them to interact with it and each other, such as activate, suspend, reactivate, and terminate a process. The entity class represents the entities within a simulation which is derived from process and has an independent thread of control associated with them at creation time, allowing them to convey the notion of activity necessary for participating in the simulation. The queue class stores the inactive simulation processes within the simulation. The simulation class derived from process, which starts and stops a simulation, schedules the simulation processes, remove the process at the head of the queue and reactivate it. In simulation models, processes are managed by a simulation scheduler and are placed on a queue the event list. SOS library is a collection of classes specialized for ship operation simulation, which are derived from the piece library. Based on the components in a ship operation system, SOS library mainly consists of ship, port, terminal, anchorage, entrance channel, arrival simulation, and entrance channel system classes as shown in. The port, terminal, anchorage, and entrance channel classes are permanent entity objects to provide services for ship entities. The arrival simulation class generates ship entities randomly according to the ship arrival pattern. The entrance channel system class, a subclass of simulation, schedules the processes of ship entities in and out of the port, makes a statistics analysis on simulation results, and outputs every ship's waiting time and berth's utilization ratio. The ship class, a subclass of entity, represents a ship entity, which is the core component of a process interaction ship operation simulation model. The primary Java classes of SIMULA are illustrated in, and it runs a simulation experiment as follows. Class ship operation simulationize the control class of a simulation experiment. It initializes and activates the ship arrival process, class arrival simulation, and initializes port resources, for example, class port, berth, anchorage, and entrance channel, and environmental conditions, for example, class current, wave, and tide, then starts the simulation experiment. Class arrival simulation generates a series of ships according to an inter-arrival time distribution. For example, negative exponential distributions, NEDs, can be used to describe the arrival process, and its density function is foot equals lambda e minus lambda t, lambda equals arrival rate, t equals inter-arrival time. Class ship performs all activities of a ship as illustrated in and records all necessary times related to performance measures. Class ship operation simulationize the control class of a simulation experiment. It initializes and activates the ship arrival process, class arrival simulation, and initializes port resources, for example, class port, berth, anchorage, and entrance channel, and environmental conditions, for example, class current, wave, and tide, then starts the simulation experiment. Class arrival simulation generates a series of ships according to an inter-arrival time distribution. For example, negative exponential distributions, NEDs, can be used to describe the arrival process, and its density function is foot equals lambda e minus lambda t, lambda equals arrival rate, t equals inter-arrival time. Class ship performs all activities of a ship as illustrated in and records all necessary times related to performance measures. UML sequence diagram for simulating ship operation in anchorage area, entrance channel, and berths. Method arrive records the ship's arrival time and initializes its attributes, for example, ship tonnage, dimensions, and cargo capacity. Method allocate berth request for a berth according to berth allocation policy and queue priority, such as first come first serve rule, longest/shortest processing time, and largest/smallest ship size. If a berth is assigned to this ship, the method records the time of berth availability and steps to method check if a 4 is. Otherwise, this ship enters anchorage and waits, method wait in anchorage. Method check if 4 checks weather, water depth, safety distance, and traffic situation for permission to enter channel as illustrated in figures 2 and 3. In case a problem exists, the ship enters and waits in anchorage, method wait in anchorage. Otherwise, it steps to method enter port. Method wait in anchorage checks the availability of a free berth for no berth assigned ships, method allocate berth, and or the availability of entrance channel for berth assigned ships, method check if 4 is. Once all states meet safety requirements, the ship leaves anchorage, records the waiting time caused by berth occupation or channel unavailability, and enters method enter port. Method enter port transits this ship to the assigned berth via entrance channel and steps to method handle cargo. Method handle cargo discharges/loads cargoes from onto the ship over a random berth service time and steps to method check if 4 os. For example, berth service time for each type of ship is fitted to an Erlang K distribution, and its probability density function is foot equals k mu k tk minus 1 e minus k mu tk minus 1. Mu equals the number of ship services per day, and k equals shape parameter. Method check if 4 checks weather, water depth, safety distance, and traffic situation for permission to enter channel and leave the port. For 1 and 2-way channels without SPAC, if the check if 4 osis roar, the outbound ship leaves the berth, travels through channel, and steps to method leave from port. For 1-way channels with a SPAC, if the channel bis available, the outbound ship leaves the berth, seizes an anchorage in SPAC, then travels through channel B, and steps to method wait in SPAC. Method wait in SPAC records the time of arrival at SPAC, accommodates outbound ship mooring, and waits until channel AI is accessible. If channel AI is accessible, the ship leaves the SPAC and enters channel and records the time of departure from SPAC, releases the occupied SPAC's anchorage, travels through channel A, and steps to method leave from port finally. Method leave from port makes the ship entity exit the port system and records its departure time. 4. Class ship operation simulation finally stops the simulation experiment, updates the turnaround time and number of inbound and outbound ships, performs necessary statistical analysis, and outputs the values of port performance indicators. This PySMSO model is verified and validated to confirm that it is correctly implemented with respect to the process of ship operation. We can use it to evaluate the port performance and then do more analysis. First, the model is developed through submodels and individually examined by a subject matter expert. Second, Tracing approach comparing the simulation results with manual calculations is used to check the logic implemented in the model throughout the development of simulation model.